Hello everybody, I am Shubham Mahesh Radkar. I, along with Nachamai Chettiar, are going to present on the topic FPGA based digital FIR filter design for ECG signals. Today, we are going to explore our project on real time ECG denoising, a critical process in modern healthcare. Our approach utilizes a FIR filter, that is, a finite impulse response filter, designed and validated in MATLAB and then efficiently implemented on FPGA or Field Programmable Gate Array. This work aims to significantly improve and study how an ECG filtering is done and what are the aspects that can be improved for diagnosing of various cardiac conditions. So, let us now start with our presentation. Let's begin by understanding the why behind our project. ECG signals capture the heart's electrical activity over time, making them an indispensable non invasive diagnostic tool that is very crucial for detecting health of heart. This help in detection of wide range of cardiac abnormalities from arrhythmias to myocardial infarctions. However, these vital signals are inherently vulnerable to the external noise pertaining from various sources from our body to the electrical noises. Imagine trying to read a faint whisper in a noisy room. That's what clinicians face with raw ECG data. Some of the common culprits which we face are power line interference, the familiar 50 or 60 hum from electrical mains, which we all are familiar, baseline wander, slow, low frequency shifts caused by respiration or subtle body movements. Now, this is also a notable factor which affects the ECG signals in long term. Muscle artifacts. Higher frequency noise from muscle contractions are very, very crucial for im- disim- affecting the ECG quality. The presence of such noise significantly degrades the signal quality, leading to potential misinterpretation and hindering the accurate diagnosis. And this can be dangerous as some of the diagnoses which are wrong can lead to unwanted spending. Therefore, effective denoising isn't just an improvement, it is a crucial pre processing step. Now, let us move on to our project objectives and scope. First, our project starts with meticulously designing the phase, leveraging the power of MATLAB. The goal here was to create a precise FR filter coefficients and then thoroughly verify their characteristics. We primarily used MATLAB's signal processing toolbox, which offers comprehensive tools like FIR1 for window based FIR filter design. We configured a bandpass filter to target the diagnostically relevant frequency range of ECG signal, specifically between 0.5 Hz to 40 Hz. Then on, we went on to Veril convert the MATLAB code into Verilog code, which is very crucial for implementation on FPGA and the consequent hardware. Then we performed a verification and simulation to check whether our model is working correctly, ideally in real life. Now, let us start expanding what we did in a MATLAB design and prototyping phase. First of all, this is where FIR filters are implemented and tested. MATLAB environment is the environment where we tested our FIR filter, the finite impulse response filters. They are the cornerstones for digital signal processing, widely favored for their inherent stability and criticality for their linear phase response. The ECG signal consists of P wave, QRS complex, and T wave. The diagnostic features of ECG rely heavily on them. Unlike other filters type, FIR filter guarantee stability because their output is finite. Weighted sum of past input samples, making them reliable for sensitive biomedical applications. In our case, ECG signal to be precise. We cascaded a low pass filter and an high pass filter to create our desired band pass characteristics. This allowed us to remove the high frequency muscle artifacts and low frequency baseline wander effectively. We selected a filter order of 151 and employed a Hamming window for coefficient generation. This choice provides a sufficiently sharp transition band for effective noise attenuation. Crucially, we utilize the fill fit function for zero phase filtering. This ensures the filtering process does not introduce any phase distortion, which is vital for preserving the original morphology of ECG signal, meaning the shape of P, QRS, and T waves remain intact, true to the heart's activity, and prevent any future mishap. The raw ECG data for simulation was sourced from MIT BIH Arrhythmia database, a widely recognized resource. We took a 5-second segment, normalized it, and then passed it through our MATLAB design filter to observe the denoising effect. As you can see from the provided MATLAB output form waveform, the noisy ECG signal is transformed into much cleaner, diagnostically clearer signal. The signal which I have provided here is the same signal which is obtained after applying the filter. This rigorous MATLAB based simulation and filtering process was a critical validation step, ensuring our filter design was robust and accurate before we moved on to the hardware implementation on the FPGA. Now, further, I would like to invite Nachamai to explore more and expand on the topic of Verilog code generation, simulation, and further implementation on FPGA part. Thank you.
So we will start with the development step one, that is the MATLAB design and prototyping. So this is what we had done. Um, Here we had this MATLAB code to simulate the FIR filter. Second is the output. As you can see, there is the noisy signal, and then after filtering it, we have the filtered ECG signal. After that, the second development step is Verilog HTL implementation. On right side, you can see the Verilog filter designed using the Verilog HTL language on Vivado software. Um, so the third step is the test bench creation and automation. The test bench is created to automate and run examples of inputs on the filter that is designed previously. So this is the test bench code. Then this is the workflow of the Vivado software. One is we create the project. Second is we elaborate the design. Then we launch the simulation, add signals to waveform, and then we analyze the waveforms. So this was the simulation that we had done. Like we have the clock, then we have the reset, the in and out. We have to manually give the values of clock and reset. So when reset is 1 for a very long time, the filter is getting initialized, and when the reset becomes 0, the filter will start filtering. As you can see, the value of out changes to 1113 after reset becomes 0. So these are the key findings and filter performance. Like we can say that the filter is quite effective and it can be improved a lot more to filter industry grade signals. And these are the temporal characteristics. For example, in this, we are using less than 10 samples of the signal because it is quite complex to design filters using a lot number of samples. So these we had also generated RTL schematics and synthesizes diagrams and stuff. So the learning outcome is that we got to explore the Verilog HTL language along with the FPGA board and also the Vivado software. It is very fascinating to see that we are able to simulate huge circuits like this on FPGA board.